Ever wondered how a computer actually learns to see a person in a photograph? I mean, really see them. It's one of the biggest puzzles in computer vision. Today, we're going to hack into that very idea and break down a classic, super powerful technique that cracked the code, the histogram of oriented gradients, or as we call it, HOG.
So let's just stop and think about that for a second. When you glance at a photo, your brain just knows instantly there's a person there. But for a computer, what is it actually seeing? It's definitely not what you think.
See, a computer doesn't see a person at all. It just sees data, a huge grid of numbers. On the left, that's what we see, a person. But on the right, that's the computer's view, a total jumble of pixel values. So the real question is, how in the world do you teach a machine to find a human being in all that numerical noise?
Well, the breakthrough, the big aha moment, came from a really simple but powerful shift in thinking. The pioneers behind this whole thing realized that if you get lost trying to look at every single pixel, you'll never get anywhere. You have to look for something more fundamental. And this is the key, right here. It's not about the pixels. It's about the shape. Forget the color of someone's shirt or how bright the sun is. What truly defines an object, what makes a person look like a person, is their basic structure, their silhouette, which is really just made up of edges and the direction they're all pointing. To capture that shape, we need something called a feature descriptor. Just think of it like a numerical fingerprint for an image. It's designed to throw away all the useless visual clutter and keep only the most important bits of information needed to identify something. It's kind of like a police sketch artist for a computer. And that, my friends, brings us to HOG. The name sounds super intimidating, I know, but let's just break it down. Gradients are just a mathy way to measure edges, how strong they are and what direction they're pointing. Oriented just means we care about that direction. And a histogram, that's just a bar chart. So all HOG does is count the directions of edges in tiny little patches of an image. That's it. Now, this idea didn't just pop up out of nowhere. The core concepts were actually patented way back in 1986. But it took until 2005 for two researchers, Navneet Dalal and Bill Triggs, to publish this landmark paper that just completely unlocked HOG's potential. It quickly became the gold standard for finding people in images for years. Okay, so how does this thing actually work under the hood? Let's walk through the HOG blueprints. We're going to go step by step and see exactly how a computer can turn a boring old patch of pixels into a unique fingerprint that screams human. All right, there are 5 main steps in the whole process. First, we'll prep the image. Then, we find the edges. After that, we count their directions in tiny little cells, adjust for things like shadows, and finally, wrap it all up into one powerful description. Let's dive in. First things first, everything has to be standardized. We take our detection window and resize it to a fixed 64 by 128 pixels. This is so important for consistency. Why that size, you ask? Well, it just turned out to be a really good aspect ratio for capturing a person standing up. By making everything the same size, we make sure we're always comparing apples to apples. And this quote from that original paper just nails the whole philosophy. It says the real essence of an object's shape isn't its color or its texture, but in how its local edge directions are distributed. It's all about the pattern of the edges. Okay, step 2. The algorithm literally scans every single pixel in our window, and for each one, it asks 2 simple questions. First, is there an edge here? That answer gives us the magnitude or the strength of the edge. And second, if there is an edge, which way is it pointing? And that gives us the orientation or direction. Now this is where the magic really starts to happen. We chop up our 64 by 128 window into a grid of tiny 8 by 8 pixel squares called cells. And for every single one of those cells, we build a little 9-bin histogram. It's basically a mini bar chart that counts up the main directions of the edges inside that little patch. So if a cell has a bunch of vertical edges, the vertical bin on its chart will be really high. But hang on, what about lighting? A strong shadow or bright sunlight can totally change how strong the edges look. To fix this, we group the cells into larger overlapping blocks of 2 by 2 cells. And that overlap is super important. It adds a bit of redundancy that makes the whole thing more stable. Then we do the most critical step of all, normalization. We look at the 4 little histograms inside a block and we scale them relative to each other. And why do we do that? Well, this step is pretty much the secret sauce.
By normalizing across a bigger block, the final description becomes way less sensitive to changes in lighting. It doesn't matter if a person is standing in a bright field or a shadowy alleyway, the pattern of their edges stays pretty much the same.
Now, of course, there are a few different mathematical ways to do this normalization. Dalal and Triggs tested a bunch and found one called L2 Heiss worked the best for finding people. Honestly, the exact math isn't what's important here. The result is what matters. A descriptor that is incredibly tough and doesn't get thrown off by lighting.
So after all that work, calculating gradients, making cell histograms, normalizing blocks, what are we left with? Well, we take all the normalized histograms from every single block and we just stitch them all together into one long list of numbers. And how many numbers is that? Well, a 64 by 128 window has 105 of those overlapping blocks. Each block has 4 cells, and each cell's histogram has 9 values. So 105 times 4 times 9 gives us exactly 3,780 numbers. That is the hog fingerprint.
A list of nearly 4,000 numbers sounds super abstract, right? But this is where it all clicks. This is the payoff. What does that giant vector of numbers actually look like? Let's visualize it.
And there it is, the big reveal. On the left, you see a normal picture of a person. And on the right, that's its hog representation. Each little line shows the strongest edge direction in that part of the image. I know, it looks a little ghostly, but look closely. You can totally make out the shape of a head, the shoulders, the torso, the legs. This is it. This is how a computer finally learns to see the shape of a person.
And this isn't just a fluke. Check this out. If you take the HOG descriptors from thousands and thousands of pictures of people and average them all together, this is the image that emerges. It's an unmistakable human silhouette, built entirely out of average edge directions. This consistent pattern is exactly what a machine learning model can be trained to look for. So cool.
Hog was a complete game changer, no doubt about it. But it didn't just appear in a vacuum. So let's take a step back and see where it fits into the bigger story of computer vision. You might have heard of another famous feature descriptor called SIFT. But here's the thing, they're built for totally different jobs. SIFT is like a detective that finds a few really unique, interesting points in an image and describes them. That's great for, say, matching 2 photos of the same building. Hog, on the other hand, creates a dense description of an entire patch, which makes it way better for detecting a general category of things, like people. Hog's success really came down to its brilliant design. It could handle lighting changes, it captured shape incredibly well, and when it came to the specific job of finding pedestrians in photos, it just blew everything else out of the water. It really became a foundational technique that laid the groundwork for so many of the complex systems we have today. And that brings us to one last, really important question. Today, we live in the age of deep learning, where AI models can just learn features all by themselves from tons of data. So, does a clever, handcrafted, meticulously designed idea like Hog still matter? Does it still have something important to teach us about the art of seeing? That's something to chew on. Thanks for tuning in.